This presentation is delivered by the Stanford Center for Professional Development.
Hey there! It's Wednesday. Oh, we are coming to the end of this fine quarter. So what I'm going to do today is I brought a Pete's cup filled with candy. We'll start with that, because that's going to be helpful. What I'd like to do is there's just a couple little bit of loose ends, some things that I wanted to touch on that have come and gone this quarter that I kind of wanted to maybe pull together and reach a little bit of closure on. And then hopefully if we have time, we'll move on to just a little bit of like, well, what happens after this, right? If you liked 106B, what do you do? If you don't like 106B, what do you do? And what kind of options and sort of future opportunities there are after this ends. So I'm going to talk a little bit about just sort of some things that are administrative. I do want to talk about the final just for a second, because it is kind of the last opportunity for you to show us your mastery of the material and get the grade that you've been working hard for all quarter. It does carry a certain amount of weight, right? 30% of the weight is in the default system is actually placed on the final, and actually more of it can move to that, right? If you have a kind of a better showing on the final than you did in the midterm, we're happy to move some of that weight over so that could actually account for even more of your total grade. So there's kind of a lot riding on it, and you want to be sure you come ready to show us the things that you know and that you have comprehension and mastery over. To note, though, I would say that it's going to look a little bit different than the midterm in terms of its emphasis, right? We are going to see a lot more of this nitty-gritty dynamic data structure, linked list, trees, graphs, pointer-based structures, right? And with the inherent complications in dealing with that kind of dynamic structure. So kind of bringing your best pointer game, right, to the exam is certainly going to pay off here. The coding that you'll see will look a lot like that from the assignments. If you already had a chance to look at the practice exam, you'll see that kind of there are themes there, right, that echo the things you did on the work. We're trying to make sure that we're kind of connecting to the effort you've put in all along. And then there'll actually be some opportunity to sort of think a little bit at a higher level about making and analyzing choices for design and implementation. I'm going to talk about that just a little bit today, because I feel like, at any given moment we're talking about how we might implement a stack and now how we might implement a queue. And sometimes it helps to step back a level and kind of think a little bit about the choices for the bigger picture of when to use a stack and queue and how to make decisions in the large about those trade-offs, right, that are intelligent and grounded. So I'll do a little bit of that today, and then some of that just has kind of been built up all quarter long. It is open book and open notes, right? You can bring all your printouts, your readers, sections, all those sort of things. For some people, that translates, though, to this idea that, well, I don't need to prepare because I'll just have all my stuff there. If I need to know something in the exam, I'll go look it up. That's certainly true for looking up details. You want to remember how this works, or you had a piece of code that was similar that you think could help you to brainstorm what you're trying to do this time. But you're not likely to have time to learn new things in the exam. So if there's something you really feel you have not got your head around, the investment up front before you come into the exam is where to kind of get that understanding in place, rather than trying in the exam to be flipping through chapter 10 trying to learn something may not really play out. I highly recommend practicing on paper in the exam-like environment, so really working the way you will be working in the exam to give yourself the best consistent prep for what's happening there. And then some people have asked about extra problems, just wanting more and more of them to work on. I'll give you a couple places where you can look for things. One is that CS106X is being offered this same quarter, and they are just the honors version of our class. So they have some slightly notched up problems, but their practice and real midterm are both posted on their website, as well as their practice final. Just serve as, they have very similar coverage, right? They did some assignments that were like ours, some that were a little bit different, but still just good places to kind of just grab actual exam problems with their solution. And then the chapter exercises and section problems often have either are old exam problems or eventually became exam problems, so they kind of come and go in terms of being used as examples or used as exam problems. So definitely places to just pick up extra mileage. Okay. So let me tell you just a little bit about, so any questions about the final? Just what to expect, where that's going. Let me talk about design just for a second, because I do feel like we have touched on these themes again and again, but maybe it's good to kind of just have at least one sort of moment of trying to pull this together and think a little bit about the closure and kind of the big picture of all these things. That a lot of what we're talking about in 106B was at the beginning was we're giving you these abstractions, these cool things to do stuff with, a map, a stack, a queue, a vector, and problems to solve where those abstractions have a role to play. And then we spent a long time saying, well, okay, now that it's our job to make those abstractions work, right, what techniques can we use? What algorithms algorithms and data structures, right, will help us manipulate and model those structures in efficient ways. And we certainly spent a lot of time talking about runtime performance, as though maybe that was maybe almost a little too much in your mind to think that was the only thing that really mattered, was how fast can we make something. If O of n is better than n squared, log n is better than n, right, kind of driving toward these holy grails of bringing the time down. It's certainly a very important factor that often, right, the difference between something being linear and something being quadratic is a matter of it being tractable at all for the problem at hand, that you cannot sort a million numbers in a quadratic sort, right, in nearly, right, the same efficient time. It really could, for large enough data sets, right, be completely infeasible. So it is important to kind of have that big picture, to be thinking about it and know about those trade-offs, and to understand issues of scale here. But we also did some stuff on the homework about actual empirical time results, which is also another way to kind of bolster our understanding that the big O tells us these things, but what really happens in real life matches it, but not precisely. Those constant factors we threw away and other artifacts that are happening in the real world, right, often give us new insights about things and challenges, right, that we're facing. We also need to think about things like mix of expected operations, having some operations be slow at the consequence of other operations being fast, right, is often a trade-off we're really willing to make. And so on the editor buffer, we kind of drove toward let's get all the operations to be fast. And in an ideal world, that's certainly the best place to be. But it's also a matter at what cost, right? In terms of code complexity and memory used and effort put into it, it may be that we're willing to tolerate some operations being less efficient, as long as the most commonly used ones, right, are very streamlined. And then things about, like, we talked about these worst cases and degenerates, about knowing when we can expect our algorithms to degrade and whether we want to do something about that, or choose a different algorithm or provide some protection against those kind of cases coming through. To a lesser extent, we already talked about memory used, how much overhead there is. So seeing that we went to a pointer-based linked list structure, we added the 4-byte overhead for every element. We went to an 8-byte overhead once we got binary search trees, and maybe even a little bit more if we have balance factors included. That those things, right, kind of ride along with our data, kind of just increasing the size and the memory footprint of it. So there's a certain amount of just kind of overhead built into the system. There's also this notion of excess capacity. To what extent do we over-allocate our data structures early, planning for future growth, in some sense to save ourselves that trouble of enlarging on demand, is kind of just preparing for a large allotment and then using it up as we find it. But then when we do exceed that capacity, having to do it again. And so where to make those trade-offs about how much excess capacity and when to do the enlarging, and has a lot to do with, well, what's our general memory constraints. And I would say that memory, right, has gotten to be quite free, in recent processors and computer systems, right? You don't really think a lot about, 100 bytes here, 200 bytes there, 1,000 bytes there, even megabytes, right? You can talk about as though it's a drop in the bucket. So this is maybe something that actually isn't given as much weight nowadays as it was 10 years ago, when there were a lot more constraints, but with the sort of move toward more embedded device programming, so looking at the iPhone or cell phones or things like that, where they don't have that same liberty to be wanton about memory, it has come back to being a little more careful and keeping an eye on it. There's also an issue here which trades off a lot with runtime performance, right, which is redundancy versus sharing. Having two different ways to get at the same piece of data often will provide you with quick access. So for example, if you have a card catalog for a library where you can look up by author, you can look up by title, you probably are maintaining two data structures. One that manipulates them sorted by title, one that manipulates them sorted by author, that in effect are both kind of looking at the same books in the end. So maybe there's a set of pointers in one map over here, indexed by author, another one indexed by, or keyed by title over there. And that means in some sense I'm repeating all my data. Hopefully I'm sharing it with a pointer, so I'm not actually really repeating the whole book's worth of data, but I actually have two pointers or potentially two or more pointers to the same book, depending on different ways you can get to it. But then that gives me that fast access. I want to know all the books written by Leo Leone. I can find them easily, as well as finding all the books that have the word king in the title, and not have to do searches on a data set that's been optimized only for one access. So definitely trades off where, more space thrown at it, right, to get at that fast access for different ways. And then this last one is one that I had mentioned on the way, but I think it's one that's easy to overlook, which is to get very excited about how fast you can make it, how small you can make it, how fancy, right, it is. Has a real downside cost in terms of how hard it was to write. that typically, right, when you go to these fancier strategies that are space efficient and time efficient, you had to pay for it somewhere, right? It wasn't for free that the easy, obvious code would do that. It tends to actually be complicated code that may use bit operations, that probably uses more pointers, that has kind of a density to it. That means it's going to take you longer to get it running. It's going to take you more time to debug it. It's going to be more likely to have lurking bugs. It's going to be harder to maintain, right? That if somebody comes along and wants to add a new operation, they open up your code and they're frightened away, it might be that code will never get moved forward. Everybody will just kind of open it and close it immediately and say, well, whatever, we'll make it work the way it is, rather than try to improve it or move it forward, because it actually is kind of scary to look at. So thinking about what's the simplest thing that could work. So there's movement actually that I think that's pretty neat to think about. There's this idea of the agile programming methodology. And it's based on the idea that rather than planning for I'm going to build the most super stellar infrastructure for just solving all the world's problems. So you're about to write a chess program. Or maybe it's even something simpler. You're going to write a checkers program. And you say, I'm going to sit down, I'm going to design the piece and the board. And then you think, hey, checkers is just one embodiment of this. Why don't I try to make the Uber board that could be used for strategic conquest or for chess or for Chinese checkers? Maybe you can have these hexagonal things, and you start building this, crazy infrastructure, right, that could handle all of these cases equally well, even though in fact all you really needed, right, was checkers, right, a very simple 2D grid. But you imagine the future needs, right, way in advance of having them, and then you design something way overly complicated, and then what happens, right, is that you get bogged down in that, and it never happens, and the project dies, and you lead a lonely death, by yourself eating oatmeal. And I like oatmeal. But so one of their models is design the simplest thing that could possibly work. And I think that's a neat gift to yourself to realize that the simplest thing that could possibly work, that meets the needs that you have, that's has a decent enough big O and memory constraint, right, that it meets your needs, and the simplest form of that, right, is going to be the easiest thing to get working and running. And if you later decide you want to go fancy, you hopefully can swap it out using the good principles of abstraction and capulation. It should be that it's independent when you decide you need that fancier thing. So I put a couple questions here because I thought maybe this would help us to just frame a little bit of thinking about these things. And these are questions that I'm hoping you can answer for me, and that's why I brought my pizza cup full of candy, because I'm prepared to offer bribery for people who help me answer these questions. So let's talk about array versus vector. So the C++ right, built an array is what is behind the scenes of the vector, and then the vector adds convenience on the outside of it. Okay, and so at some point I had said early on, I said, well, once I tell you about array, just, put that back in your memory and just use vector instead, because everything array does, vector does nicely and cleanly, and it adds all sorts of features. For example, somebody give me a list of some things that vector does much better than array that are worth kind of... Way in the back, Clinton.
Bounds checking.
Bounds checking. What else? Well, a blow pop is on the line. I hate to interrupt your, come on, help us out. You got bounds checking, what else?
Oh, more?
I want more.
First thing off the top of my head.
Come on, you got nothing else for me?
I don't even want a blow pop.
You don't even want a blow pop? All right, well, I'm going to give you a blow pop. I'm going to give your blow pop to somebody else. Right here, I'm going to give the blow pop to you. Tell me what makes vector good.
It has operations that shuffle elements for you.
Yeah, it does the insert and delete, moving stuff down, right? It also does the growing, right? You keep adding and it just grows, right? Raw arrays don't do that. You want a raw array to grow? You grow it. You take the pointer, you copy stuff over, you delete the old one, you rearrange things, right? You do all the work. So vector buys you kind of array with benefits. And so it seems like that then you could kind of take away the naive point would be like, well, just use vector. Always use vector. Vector's always better than array. Is there ever a situation where array still is a pretty valid choice? What is it that array has that maybe vector doesn't?
Well, when you add things dynamically to the vector, it actually doubles the size rather than just increasing it by 1. You know the exact size and you know it's not going to change. You're using up less memory.
That's one of its big advantages. If you know you only have, let's say you have some reason to know you have a very small array planned for. So the one on the practice exam was, well, if you were doing a calendar where you had the 365 days in the year and you're keeping track of the events on a particular day, you know how many days in the year, there's never going to be any change in that. Well, there's leap year, but whatever. It's okay, 366, right? But you know that, and you know that in advance. So why fuss with a data structure that does all this growing and shrinking, and in a sense has some overhead associated with that, when in fact you know there's exactly this number, that's all you need. And in fact, it's almost a little bit more convenient to set up, because you can just declare it that size and it's ready to go, whereas with the vector you have to go through and add all the elements to kind of fill it out and do stuff like that. So there are a few situations where, yeah, you might just say, I don't need the advantages. It adds some overhead that I don't want to pay, and I'm perfectly happy, just making a small fixed array. You'll still lose bounds checking, but if you are being careful, maybe you're comfortable with making that trade-off. And then by losing bounds checking, you actually are getting a little bit of a speed improvement back, because the bounds check does actually cost you a little bit on every vector access that an array would not actually pay. Now that's really in the noise for most programs. I hesitate to even mention it to even get you thinking that it matters. But it is part of the thinking of a kind of a professional programmer sometimes, is that may be the thing that comes down to making your operation constant factors streamline enough for the operation you need. So I put here stack and queue versus vector. Given that stack and queue are really kind of just vectors in disguise, right? And they're actually, in fact, vectors with less features, vectors that can't do as much. That one of the implementations for stack and vector could easily be just layered on top of a vector. It's like, why is it good to take away things?
Keeps the user from tampering with the contents of the vector.
So it's enforcing kind of a discipline, right, on how you use it, right? That stacks are LIFO, queues are FIFO. The way things go in, the way they go out are very rigid, right? And by using stack and queue, you are guaranteeing that you won't go in and accidentally put something at the head of the line or remove something out of the middle of the stack, because you just don't have access to that, right? It's been tidied up and packaged up into stack, which has push and pop, queue, which has NQ, DQ. No other access implied or given, totally encapsulated from you. So in fact, it allows you to kind of like maintain, right, a discipline that otherwise, right, the vector didn't strongly provide for you. Question? Yeah.
Benefit. Another thing you can do is you can optimize a stack or a queue to be very good at the only things you're doing, which is just pushing and popping or queuing and dequeuing.
I think that's worth a smartie, don't you? I think that is. Oh yeah, exactly. Right. So by restricting what you have available, it actually gives you choices in the implementation that actually wouldn't have worked out as well when you had to support the full range of operations. It's exactly true. Stack and queue only adding from one end mean that things like a linked list, which isn't a good choice for implementing the general case of vector, are perfectly good choices, right, for the stack and queue case. So giving ourselves like some freedom as the implementer and some information about how it's being used can pay off. It also means when you read code, if you see code that's using something called a stack or using a queue, you immediately know how it works. You can say, oh, look, here's this search that's actually stuffing a bunch of things into a stack. You can say, okay, well, then I know they're going last in, first out. If you see them using a vector, you have to actually verify, okay, well, where do they put them in the vector? Where do they pull them out? Like the code doesn't tell you the same things. It doesn't tell the same story as it does when you see a word that has a strong meaning to it, like stack and queue. So there's generally these choices you have to make about like sorting things or not sorting things. We spent a long time talking about sorting, right, and how various algorithms sort of approach the sorting problem and what they come up with. I have a question here. What sorting algorithm is best? What sorting algorithm is best? Is there an answer to that question? Why would I ask a question that has no answer?
Depends on what you expect to be giving it.
It depends. That's a great thing. It depends on what you expect to be giving it. Like, how big is it? What are the contents of it? Is it random? Is it sorted? Is it almost sorted? Is it reverse sorted? Is it, drawn from a range of 1 to 1,000 values, or is it drawn from 1 to 3 values? Right? A huge array that had just 1, 2, 3 in it, right, might necessitate a different approach than one that has 1 to max int in it. So there is no answer to that. It depends. It's like, well, it depends. What do you know? If you don't know anything, give it to someone else. This is a chain of good luck here. Is that if you don't know, right, there's certain things that perform well, in the average case and don't have degenerate behaviors. For example, heap sort is a great sort for kind of the general case of an n log n that doesn't use any space or any extra space the way merge sort does, doesn't have any degenerate cases, and kind of for a unknown set of inputs works pretty well. But if you happen to have a little bit of data like, oh, it's almost sorted, insertion sort, and even Barack Obama's not favorite bubble sort has a chance of being in the run when it's already sorted. Sometimes you have this thing about, well, is it worth sorting, right? And calculating the payoff. We had a problem on a sections exercise once that I think is a really good one to kind of think through and revisit this idea of, well, certain operations, many operations are actually much more efficiently implemented if the data is sorted. right? You can think of them off the top of your head, like, oh, you want to have the minimum? Well, if it's sorted, it's very easy. You want the maximum? It's very easy if it's sorted. You want to find the median? Also, right, very easy if it's sorted. You want to find duplicates, right? Once they're sorted, they're all lined up together. You want to find the mode, which is the most frequent element, right? Also easier if it's sorted because they'll all be grouped together and run. So you can actually do a linear pass, kind of counting what you see to find the longest run. If you had two arrays and you wanted to merge them or intersect them to find their common elements, much easier if they're sorted. All these things, right, that are hard to do when the data is in totally random order actually kind of have much more streamlined algorithms once you invest in sorting it. And so there was a problem there. It was like, well, how do you know when it's worth doing that? If you only plan on running one merge and you could do it in n squared, is it worth it to sort it n log n so you can get an ON of merge? And it's like it has a lot to do with, well, how often do you plan on doing the merge? How big is your data set? What are your constraints on the times there? But it is interesting to think about that relationship, right? That it isn't for free, but it actually has potentially, it's like an investment by sorting it so that you can do a lot of fast searches later. This one actually is kind of interesting because they actually solve a lot of the same problems and they almost differ in only one small way, right? Which is if you had a set, so set is being backed by a balanced binary search tree, so it actually is a sorted data structure internally, versus a sorted vector. And so if your goal were to keep track of, all the students at Stanford and you want to be able to look up people by name, right, then the contains operation of the set is actually doing a binary search traversal to find it, the binary search on a sorted vector using the same path but working through a vector. And so we can make the searching operations like contains and other sort of lookup-based things logarithmic in both cases. Okay, so what advantage, right? So set, and sorted vector, would I just use them interchangeably? Is there something one can do the other can't, or some advantage or disadvantage that's assumed in that decision? Over here, Madeline.
You don't have duplicates in set, but you can have duplicates in your sorted vector.
So certainly, like set has another concern, just how it operates. It's like, oh yeah, you can't put duplicates in. So if you have two students with the same name, then in the set, it turns out, yeah, you're all coalesced down to one. Your transcripts all get merged to your advantage or not. What else does set buy you that sorted vector doesn't? How hard is it to edit a sorted vector? Right, you want to put something new in there? You're shuffling. You want to take something out? You're shuffling. Right, the movement to the pointer-based structure there, the binary search tree behind this, is giving us this editability of the data structure. Right, the convenient logarithmic time to remove and add elements, right, using the pointer wiring to do that, that the sorted vector doesn't have. Now, that trade-off, right, is actually one though that the kind of the situation may be that you just don't do a lot of edits. And that's actually a very common situation, right, is that the sorted vector happens to be like, I think, a very underutilized or underappreciated arrangement for data, because in fact, actually for most things that actually aren't getting a lot of edits, that having a linear time edit isn't actually going to be a painful consequence, and yet you're doing a lot of searches and you're getting the binary search there where you really cared about it with no overhead, very little overhead, a little bit of excess capacity, but none of the pointer-based trouble, right, that came with the set. So the set actually adding on to that another 8 bytes, potentially maybe even a little bit more of overhead on every element, right, to give us that editability that maybe isn't that important to us. So if you're looking at that thing, you're saying, oh, I'd like to be able to have kind of a sorted structure. For example, both the set and the sorted vector let you access the elements in order. The iterator of the set goes in sorted order, going from 0 to the end, or the sorted vector gives an order. So I can browse them in sorted order. I can search them using sorted. And where they differ is, okay, what does it take to edit one? And the one that invested more in the memory had faster editing. The PQ. This is kind of interesting. The PQ is also is kind of a sorted structure, but not quite. It's a much more weakly sorted structure. So if you're using the binary heap like we did on the PQ assignment, it does give you this access to the maximum value and then kind of a quick reshuffling to pull out the next maximum and so on. But it doesn't really give you the kind of full range. For example, if you were looking for the minimum element in a PQ, where is it? It's somewhere in the bottom. It's actually on the bottommost level, but like where across the bottom? no knowledge, right? It could be in any of the leaf nodes that are at the bottom of the heap. So in fact, it gives you this access to kind of just a partial ordering of the data that's in this case is the one that is relevant for the prioritization, but not the kind of full form of sorted the way a vector is. So for example, a PQ doesn't give you things for like finding duplicates or finding the minimum or doing the mode is not actually an easy operation because you have it in heap form. It's just I can get to the max quickly. So if I cared about kind of pulling them out in sorted order to browse them, I could stuff things into a PQ and then pull them out. But what's interesting about that is that requires destroying the PQ. That the PQ isn't really a place you store things and plan on using them again. It's a kind of a place that you stick things in order to get them out in an order. That its only sort of value is in the dequeuing of them, pulling them out. So finding the most promising option to look at in a search, or finding the most high priority activity to take on or something. But it doesn't really have the proper, like if I wanted to be able to kind of just look at all the students in my class in sorted order, it's like, well, I could stick them in a PQ and then pull them back out. But it's kind of funny. I put them all in the PQ just so I could pull them back out. It wasn't a good way to store them for that browsing operation to be easily repeated. If I put them into a sorted vector, then I can just keep iterating over it whenever I need to see it again. And so a lot of the things that kind of come down to is having a pretty good visualization of what it is that going to a pointer-based data structure buys you and what it costs you, right, relative to the contiguous memory. That's one of the tensions underneath most of these things is like, well, putting more memory into it by virtue of having a pointer wiring as opposed to a location arrangement, that there's no information that is stored to get you from array sub 0 to array sub 2. They're just contiguous in memory, and so that saves you space because you only have to know where it starts and just access contiguously from there. This pointer means there's more traversals, there's more memory, there's more opportunity for error, but it gave you this flexibility. It broke down this contiguous block that's kind of a monolith into these pieces that are more flexible in how you can rearrange them. And so kind of having these pictures, like being able to think about these things is actually, I think, a kind of important skill to come away from 106B that, oh, okay, yeah, there's never one right answer. That you're investing in this to solve this other problem, and there's going to be downsides. There's no kind of just obvious triumph over all, it's fast, it's cheap, and it's small and easy to write solutions out there. So I put up here I had to winnow this down to what I thought were like maybe the 5 or 6 things that at the end of 106B, I want you to feel like, oh, okay, that's what I got. That's the kind of core heart of gold. So I call them the MVPs, the most valuable players of the CS 106B curriculum here. That if you're kind of looking back on it and you say, well, where did I start? Where did I end up? And how did my knowledge grow in the meantime? And I'm hoping these are the things that stand out for you. Is like, okay, yeah, that was a real growth area for me. One is the idea of abstraction. And that was certainly stressed early on where it's like, okay, well, here's a stack, here's a queue, here's a map, here's a set. They do things for you. We don't know how they work yet, but just make cool things happen with them. So solve maze problems and random writers and do neat things with dictionaries without knowing kind of how they work. And so you're leveraging existing material right without knowledge of how it works. It helps you keep the complexity down. And you can solve much more interesting problems, right, than you could have without them. Like try to go back and imagine the Markov random writer problem. And now imagine doing it without the hash table, right, without the map in play. So if you had to kind of figure out, okay, well, given this character, go look it up and find a place to store it with its, and then actually store, okay, the character in some other array that was growing kind of on demand as you put stuff in there. And it's like, yeah, you would never have completed that program, right? You would still be writing it today, kind of having pointer errors and whatnot behind the scenes. That having those tools already there, it's like having the microwave and the food processor and you're about to cook instead of actually having one knife, a dull one, and just doing all your work, right, with a dull knife and a fire, right? It's like, oh, you actually have some real power there. Recursion, sort of a big theme in the weeks that followed that, right? How to solve these problems that have in them this self-similar structure, looking at these exhaustive traversals and choice problems, right, that can be solved with backtracking. And so having this idea of how to think about things inductively using the recursive problem solving and how to model that kind of process using the computer. A very important kind of thing that comes back again. Then we look at algorithm analysis, right? This idea of making this Big O, so the very sloppy math that computer scientists are fond of, talking about the scalability and growth, knowing about curves and kind of the relationships and how to look at algorithms in a more formal analysis sense, right? Still, in this case, there's actually quite a bit more formalism to this than we really went into, and if you were to go on in CS and look at it, you will actually see there's quite a lot of rigor that can be looked at in that area. We were kind of getting more just an intuition for how to gauge things about algorithms and their growth. And then this backside, right, all about implementation strategies and trade-offs. So now that we've benefited from those abstractions and we've solved some cool problems, what's it like to actually be the person building them? What are the techniques? What does it take to wrestle a pointer or a linked list or a tree heap graph into doing something really cool for you? And then how does that inform sort of your information, what you expect about its big O and the coding complexity that was inherent in achieving that result. And hopefully, right, in continuing with the theme that 106A started with you on, was just this appreciation for design, that in the end, getting code that works, that's ugly, just isn't hopefully where you're satisfied with, that you really want to approach problem solving in this way to say, produce beautiful, elegant, unified, clean, readable code that you would be happy to show to other people and be proud of, right, and maintain and live with, the kind of work that other people you would work with, right, would appreciate being involved with. And then I put things that I'm not so much, like I don't think it's the most valuable players, but part of what kind of came along the way, the idea of pointers and C++ being one of the, C++ and its pointers, maybe they're kind of one and the same. It's like we choose C++ for our language, so as a result, we get to learn some C++. Because C++ is so heavily invested with pointers, right, we also have to do some practice with pointers to kind of get our job done. So I think of those as being like, off to the side. I don't think of them as being on the platform of things I worship, but things that need to get our job done. I did put a little note about pointers here just because there was quite a lot of comments on the mid-quarter evals that said, pointers still scare me. Pointers make me crazy. I don't know enough about pointers. Here's a fact for you. You'll probably never feel like you know enough about pointers. Today, tomorrow, 10 years from now, right? You'll still kind of feel like, wow, there's some real subtlety and trickiness in there. They're an extremely powerful facility, right, that gives you that direct control over allocation and deallocation and all the wiring and sharing that is important to building these complicated data structures, but there are so many pitfalls, as I'm sure you've run into at least, most of these, if not all of them at some point, right, where you've mishandled a pointer or failed to allocate or deallocate, and the way it gets reported, right, whether the compiler or the runtime error that you see is helpful in sorting it out, is actually kind of a real cause for long hours to disappear in the name of mastery of this. If you're still wary of pointers, you probably should be. Right. Think of this as this is your first go around. Right. We're still at the kind of journeyman stage for programming here, and so although there were pointers in 106A, they were very, very hidden. Right. This is the first time you're really seeing it and exposed to it and trying to get your head around it. If you go on to 107 and 108 and things like that, you'll just get more and more practice, and so it will become more solid as you kind of keep working your way through it. But at this stage, it's actually okay and probably pretty. Commonplace to feel still a little bit. You see the star and you kind of take a double take. That's probably just where you should be. Think spicy, just like this on the Chinese restaurants, right? They put the little red star by food you want to be careful of. That's why they put the star for the pointer. And so then here was what I thought. I actually also wanted to kind of even zoom out, even just farther, which is like a decade from now, right? When you are thinking back on the whole of your education and what you learned, it's like, well, do I want you to really remember, how to use the type name keyword in the C++ generic, template facility? No. Actually, if you code in C++ every day, great, you'll know that. And if you don't, you can forget it and it's long gone. What I hope you'll carry away from you is a couple of kind of concepts that kind of broaden behind, outside of CS, right? One is just this idea of algorithmic thinking, like how you approach something logically and stepwise and draw pictures and analyze it to understand the cases and to debug when things aren't working well. I think that's a skill that actually transcends the art of computer programming into other domains, just any kind of thinking logically and problem solving and analyzing in that way. I also hope that some of the experimental things we do with the sort lab and the PQ and some of the big O and the kind of the things we try to do in class together help you to be comfortable with deciding back of the envelope calculations. And this is something I'm kind of a little bit of it's a pet issue of mine, which is, I think in the era of computers and calculators and whatnot, it's really easy to get distance from numbers and start thinking, well, I just punch numbers into formulas and then one comes out, right, must be the truth, right? And then not having any intuition is whether that's the right number, whether that number makes sense, whether that number actually is grounded, and whether you've actually are an order of magnitude or so off because you've actually made an entry error and you don't even notice it. And so becoming comfortable with this idea of like using those numbers to drive things, being able to take some time trials, do some predictions, do some more time trials, kind of match those things up, do a little sketching on your numbers and see that kind of things are working out and feel comfortable kind of having the math and the theory reinforce each other, and not get too distanced from the fact that those numbers actually do kind of play out in the real world in ways that are interesting, and not just let the numbers themselves tell the story, that there really is more to kind of connect it up with. And then this idea of trade-offs. You may not remember how you can write a linked list, or how a hash table kind of does the things it does, and how to get one working. But hopefully that you will take away this idea that the answer to most questions begins with the phrase, it depends. If I say, if it's better to use a hash table or a binary search tree, the answer will be, it depends, right? No, it's always better to use this sort. It's always, wrong to use this approach. It's that it depends. Do you already have the code written for that and it works well and you don't care how long it takes? Then bubble sort actually could be the right answer. Barack Obama notwithstanding. But knowing whether memory is at premium, whether time is at premium, what your mix of operations are, what language you're working with, what programmer expertise you have, what timeline you have for developing it, all can play a role in deciding what choices to make and what strategy to pursue. And so just being very comfortable with this idea that, well, it's about gathering information before you can commit to one strategy, as opposed to being, it's always going to be this or that. All right, so that's kind of the 106B thing. I have a couple little slides here on things that happen after 106B. And I'm just going to go ahead and show you. And this would be a great time to ask questions, in particular if there's anything kind of you're curious about, where we go from here, and how to make good decisions about things that follow. The most obvious following courses, right, from CS. So if you took 106B and you hated it, I'm very sorry, and hopefully the scarring kind of will heal over and you'll lead a productive and happy life elsewhere. But if you did like it and you think, oh, I'm kind of interested in this, what do I do next, right, to kind of explore further? Where else can I go with this? I put up the kind of intro courses right here with their numbers and their names, and I'll talk a little bit about what each of these does to kind of give you an idea of what opportunity it offers to you. The obvious kind of follow on to the programming side. So 106A and B are programming courses, building your programming mastery. That 107 follows in the same vein. We typically call those systems courses in CS nomenclature. So that means practical, hands-on programming, kind of getting more exposure to the system. So 107 builds on 106B's knowledge in a class called Programming Paradigms. Part of what it's trying to explore is different languages. So you actually look at the language C, kind of stepping back to old school. You look at the language Scheme, which is a functional language that kind of was developed for AI purposes, that has a long history coming from the math side of things. Probably looking at some sort of scripting and sort of flexible language like Python. We kind of mix them up a little bit, so it's not always exactly the same things, but kind of looking at other languages, other ways of doing things. And the other component of 107 is also looking at some more low-level things, which is what happens, when you pass your code off to the compiler, what is it doing? What kind of analysis does it do of your code? How does it actually generate machine code? What happens at the machine layer? Understanding some more of the low-level performance implications and how things are expressed. Getting a better understanding of pointers certainly comes up in this place because there's actually a certain amount of low-level coding that's being explored in this class. And so just kind of building on the programming skill, it has, you move toward a Unix, Linux-based environment, so away from the Mac and Windows. And just continue building larger programs, right, with more complicated features to kind of just grow your mastery. Internally, we actually call this class kind of programming maturity, even though that's not its title. But we see it that way in the sequence in terms of just kind of growing you into a more versatile programmer, seeing different languages, different things, and kind of just getting more understanding of what happens under the hood. It is a 5-unit class, right? It's typically offered fall and spring. Most people think it is about as much work as 106B, sometimes a little more, a little less in different parts of the quarter, depending on kind of what your background is and how 106B worked for you. But kind of in a model, I think most people think of it as being, would you guys say, like 107? About as hard as 106B? Some weeks it's harder, some weeks it's not. Maybe that's the deal. The 108 class, which actually it follows onto 107, but that prereq isn't particularly strong, is a Java class. So moving in the other direction, rather than moving down an abstraction, moving up in the abstraction, looking at more large-scale design, modern programming technique, using object-oriented facilities, kind of thinking about large-scale program. You do a big team project in the end, so a 3-week, 3-person massive effort that is kind of the first really big scale thing that you'll be exposed to in the lower division curriculum. Quentin.
7?
So there is sometimes a 107L, which has some relationship to the 106L in the way that it's like, oh, there's more hands-on, sometimes more C++ and stuff like that. I don't know whether it will be offered this spring or not, but if you look in Access, it will tell you at least whether we have it tentatively on the schedule. I think that kind of comes and goes with the interest from the students and the availability of someone to teach it. Brad.
Are the lectures available online for 107, so can we watch some and see what it's...
Yeah, so 107 is offered and 108 are offered on TV usually once a year. 107 is offered on TV this spring, so in fact the one in fall is not taped. So there might be that the old lectures from spring are somewhere around that you could dig them out, but I don't actually happen to know for sure. 108 is on TV, I think, in the fall, not in the winter, so the fall lectures are probably still around for at least 108, so you could take a look at them. You can certainly look at their websites if you just go to the cs107.stanford.edu, cs108.stanford.edu, and there's often a lot of old materials and handouts and stuff that gives you at least some idea of some of the things that have been covered, you know, in the most recent offering of it. And certainly, like, just showing up in the first week is one way to get kind of a idea of what you're in for. 108 is a 4-unit class, and because it's in Java, there's certain things about Java that just the safety and the kind of attentiveness to the compiler makes the error handling, I think, just a little bit easier. So I don't think most people think of 108 as quite as intense as 107 or 106B, but that project at the end has quite a reputation for kind of being a real time sink. So it has lots to do with just being scheduling and kind of keeping yourself motivated and working through that team project at the end is, I think, where most people find the big challenge of 108. And then on the math side, right, so in the nomenclature CS, right, we also have this idea of theory, introducing you to more about the formalisms for big O and discrete structures and doing proofs and thinking about logic. And so we have a 103 A and B and a 103X, which is a combined accelerated form of A and B, which serve as kind of math classes. They really are math classes, right, for introducing the kind of mathematics that's important for computer scientists. So that is, for people who are thinking about a CS major, another very good course to get in early, because pretty much everything in the upper division of the CS major has these things layered down as prereqs. So these are kind of the intro courses that serve as the gateway to prepping you to go on, and then look at things in a more topical way. So looking at networks or security or HCI or artificial intelligence kind of layers on a grounding in theory and programming that came from the intro courses. Okay, so that said, we're in the midst of a really serious curriculum revision, which is on kind of on the table and being designed right now, and then was voted on by our faculty yesterday and approved, and has to go through the School of Engineering and get approval, and then there's going to be a little bit of jostling as everything kind of gets worked out. But starting next year, actually, you're going to see some changes in the department, where some of these courses are kind of going to get morphed, and they won't be exactly the way they are today. That doesn't, as a Stanford undergrad, you actually have the option of graduating under any set of requirements that are in play anytime you're an undergrad. So you could graduate under this year's requirements if you wanted to jump right on, or you could wait. I think for most students the right answer is going to be to wait, because I think the new arrangement is actually much more student friendly. It has more flexibility in the program right now. If you look at the CS program as it is, it has a lot of pick one of two, pick one of three, pick one of two, where you're very constrained on what you can choose. And the new program actually is going to be more track-based, where you pick an area of interest. You say, I'm really interested in graphics. You do a little depth concentration in that, and then just have room for a very wide selection of electives to fill out the program, as opposed to kind of a smorgasbord where we've kind of forced you to pick through a bunch of different areas. So for most students, I think it actually just gives you flexibility that actually gives you the options to pick the classes that are most interesting to you and kind of get the material you want. It's kind of a growing recognition of the fact that CS has really broadened as a field, so that in some ways our major looks the same way it did 10 years ago, kind of a classic sort of definition of, well, here's these 7 things that all matter, and it's like the things aren't 7 anymore. There's now 15 of them, 25 of them, right? If you look at the spectrum of things that computer science is now embracing, that we can't say you have to take one of all these things without keeping you here for 8 years. And so we are allowing that our field, kind of its footprint has gotten so large that we need to let you pick and choose a little bit to get the slice that seems most appropriate for where you're headed. So you'll see more about that. If you are not, if you are thinking about being a CS major and have not yet declared, I would advise that you add yourself to what's called the Considering CS list, and you can get to this from the CS Course Advisors page, which off the top of my head, I think it might be CS Advising, but I'm not positive. I'll put a link on our webpage when I remember what it is. But it is a mailing list, so we have a mailing list of the declared undergrads, but we also have a list for people who just are at least potentially interested in the major and just want to be kept up to date on things that are happening. And there's going to be, I think, a lot more activity on this list in the upcoming months as we kind of publish the information about the new curriculum. So that you'll just know, kind of what's coming down the pike so you can make good decisions, preparing for what will be today and what the transition plan will be as we move into the new courses, and how to make sure you, land in the right place when all is done and said. And then I put a little just note about other majors, right, that exist, right? So CS is the home base for kind of people who are solving problems using computers, right, which spans actually a large variety of people doing a lot of different things. And then there's a couple other majors, right, that we participate in the interdisciplinary sense that use CS as part of a larger context for doing things. So computer systems engineering, which is between us and EE, which is a little bit more about hardware. The symbolic systems program, which is run by linguistics and includes cooperation from psychology, philosophy, communication, and CS, right, looking at kind of artificial intelligence and sort of modeling human thought and understanding about intelligence and whatnot as expressed in that way. And then there's a mathematical and computational science program that's come home to the statistics department that is joint between math, computer science, and the MS&E that's looking about, it's more about kind of an applied math degree, so taking mathematical thinking and using computers and statistical things to kind of analyze and think about things. A lot of financial people end up kind of being drawn to that particular one, or people who are doing kind of risk analysis or that sort of combination of things. But where CS has a role to play in all of these, because actually it's a great tool for solving these kinds of problems. So different ways to get at different pieces of the major. And I put a couple of notes of things that I think are worth looking into in case they at some point are the right thing for you to look at. Section leading, so joining the 106 staff and shepherding the next generation of students through the program is just a great way to kind of just strengthen your own knowledge. There's nothing like making sure you understand recursion as to trying to explain it to someone else who doesn't understand it. Can really do a lot for kind of the personal connection to you and your craft, as well as just being involved with a great community. The section leaders are a really wonderful, dedicated group of students who are fun to be around and great people to make friends with, right? So I highly encourage you to take a look at that. We interview for that every quarter, so usually about week 6. We put out applications and bring people in for interviews, and it's always looking for new people to join on a quarterly basis. There are research opportunities all around the campus. One that the CS department sponsors in particular is their Curis Summer Institute, so matching professors with undergrads to do work in the summer for slave wages. But great opportunity to kind of get started on thinking about how research might be part of your future, right? And one of the best preparations for thinking about grad school. We do have an honors program, like most, where you kind of have a chance to stake out on an independent project and show your mettle. We have a co-terminal master's program where you can get some of the depth that before you leave this place. And then I just put a note here, it's like not to mention there's like a million fabulous things to do at Stanford, right? Getting involved with the arts or nonprofit organizations or sports or the student leadership or whatever that. And perhaps maybe the most important sort of memory I have from my undergrad was that the trickiest part of Stanford was actually learning what to say no to, realizing that there are 10,000 fabulous, worthwhile opportunities, and doing all of them only means kind of sacrificing your sanity and the quality of the things you do. So trying to be careful and thoughtful about choosing the things you do and embrace them. And being okay with saying, I won't do this, even though it's great to go overseas and I really would have liked that opportunity, it's not going to fit, and I'm okay with that, and don't beat yourself up over it, and cause yourself too much grief trying to do too many things. So anyway, so I won't be here on Friday. Keith is going to come. He's going to teach you about C++ in the real world. I'm going to see you guys Friday at the final, and I think that's all I need to say for today. So, okay. I have Smarties.